Hi guys, in this video I want to talk to you about thermal energy. So sort of a quick recap where we've come so far. We've been talking about energy associated with objects. So if an object's in motion, the kinetic energy associated with the motion of this entire mass. So you see over here on the left, that's what we think of as the macroscopic energy. There's also associated with this object microscopic energy. So if you're to look at the atoms, they're jiggling, there's kinetic energy associated with them, and you can see that they have different kinds of bonds with each other. So there's an energy associated with those bonds. We call that potential energy. We've come up with the microscopic energy is most relevant for us when we're talking about objects, let's say coming to rest. I have something moving and it slows down and comes to rest. Where did this macroscopic kinetic energy go? Well, what we've been calling it so far is thermal energy. And if you were to kind of zoom in a little bit, if you think about the molecular interactions, you've got that sort of, rubbing of molecules against each other, this springiness. There's all kinds of interactions going on. It's not very simple. Overall, we just say it's going from that macroscopic to that microscopic storage mode, thermal energy. So a few key points here. That energy is split between both objects. We would detect this as a temperature change in the object that's moving and coming to rest, and also the surface that it's sliding on. And I wanted to make a few mentions. There's a fuller discussion of this in the reading that I linked to, but basically, you might see in some textbook problems, especially our textbook that we're using, for you to solve for the work done by friction as something comes to rest. So technically, it's not work because all that energy hasn't left. The energy from the kinetic is sort of split between the thermal energy of the object that's coming to rest and the surface. It's split between both of them, and it's not an equal split. We don't know how to divvy that up. So that's technically what's going on, but in actuality, like what they're really asking you to solve for is to basically treat thermal energy as work, and treat it as if it's all leaving the object in motion. It's not technically correct. You can see a fuller discussion from the textbook by Randy Knight to kind of piece that all together. For our purposes, what you should know is that the thermal energy is stored in both objects. And when you're looking at a problem that's asking you to solve for the work done by friction, you can essentially use E thermal is equal to force of friction times the path length. Delta S here is the path length. Okay, so here's some visuals to help you see what's going on. So this right here is a thermal image of a bike that is coming to rest. It's braked. It's braking. You can see this red streak over here is where there's that temperature increase. And it's also a temperature increase on the bottom of the bike. So this is like detecting the temperature changes. That's how we would pick up the thermal. It may be a little bit hard to see here, but there are two 1 kilogram weights. The one on the right, the one on the right is 1 kilogram, and the one on the left is 5 kilograms. And when they slide across the floor, the larger weight has the larger change in thermal energy. It has the larger thermal energy because it has a heavier mass. There'd be more kinetic energy to start with for a given speed and more thermal. Okay, I want to show you some quick videos. So here's like a setup. This is a lead sphere, and I want to show you a video where they drop it. Again, this is through the thermal camera. Oh. So you can see it's a small temperature change, just a few degrees, and it dissipates pretty quickly. But a key thing to recognize is that it's not just on the surface. The sphere itself also heats up. A dramatic effect is when you take two small steel spheres and smash them against each other. Can you see what's going on? Do you see what just happened? Those spheres, when they collided, they actually burned. There's enough thermal energy to burn a hole through the paper. The point of contact was small enough that the thermal energy was concentrated enough to burn the paper. So you can see the burn marks. And if you did this in person, sorry, you can't, but if we did this in person, you'd even be able to smell it. When you do it on aluminum foil, you get this interesting pattern of concentric rings. I'm not really sure why that happens. Some kind of like heat shockwave effect. So key idea here, this is really important. During a collision, kinetic energy turns to thermal. Not all collisions are like that, but most in the real world are. A few more examples. This is jumping from a chair. This is a collision. Not quite as dramatic. And again, the thermal energy dissipates quickly, but there is an effect there and it is noticeable. And then here's a nice little video of a ball bouncing. Tennis ball. Cool. So that's thermal energy. One of the key takeaways for you to take away from this video, during collision, energy goes from kinetic to thermal. Hope that was helpful. See you guys around.